Bismillah ar-Rahman ar-Rahim. We started to talk about link state routing protocols, and we talked about the main characteristics of the link state routing protocols using the triggered updates for link states in a form of flooding, and that requires some memory consumption and some computational requirements and so on, and it has some effect on the bandwidth utilization, at least at the start. So there are certain characteristics. So today, inshallah, we'll talk about one example of the link state routing protocols, which is OSPF. So you'll find some similarity between OSPF and EIGRP, because as we said, EIGRP can be considered like some kind of a hybrid protocol between distant vector and link state. So you'll find some similarities between OSPF and EIGRP, but pay attention to the differences as well. So like all the other routing protocols, especially EIGRP, we use the MAC header, and in most of the cases, the MAC header contains a multicast MAC address. So though someone might say, okay, so we use flooding is supposed to be broadcast, but here we're using multicast. So we'll talk about why we use multicast as an address here. So the IP packet header also uses the multicast IP address. And then there is a transport layer header, which is the OSPF packet header. And similarly to EIGRP, OSPF uses its own transport layer protocol, which in many cases uses reliable and unreliable. In fact, here, in many cases, it uses unreliable from the transport layer point of view. However, we see that one of the application messages is link state acknowledgement. So in fact, OSPF provides reliability not from the transport layer, but from the application layer. Okay? But the packet header itself, OSPF packet header, does not contain any acknowledgement number or something like this. But the reliability is achieved through application layer protocol. So the packet header contains the router ID and what we call area ID. Area ID is similar to autonomous system number in the case of EIGRP, but the area ID has different meaning. For OSPF, the autonomous system itself is divided it's subdivided into what we call areas. Okay, and we'll talk about why we need to do that. So an autonomous system can be subdivided into 2 or 3 areas. And of course, there is the type code, which corresponds to the opcode in the case of EIGRP, which has one of these 5 types. It has the type 1 for hello, type 2 for database description. We'll talk about what this means. And then link state request, link state update, link state acknowledgement. So these are the type messages that OSPF uses. And of course, in the IP packet header, there is, remember, in network 1, there is a protocol number. And this protocol number, of course, in that case, is not TCP, is not UDP, is not ICMP, it's a OSPF. Okay, and the OSPF in that case has a protocol number of 89. You don't have to memorize it, it's a specific, because it uses its own transport layer protocol. So these are the message types in the case of OSPF. Again, similar to EIGRP, we have hello messages. Hello messages, as we said before, it's always broadcast and periodic. And this is to discover and establish adjacencies, discover neighbors and establish adjacencies between the one node and the nodes around it. So once we know that we are neighbors, so you have router 1 and you have router 2. Each router will have its own link state database, which initially it contains the link states of the directly connected network, صح? Initially, right? So what will happen is that once we establish adjacencies and we know that we are neighbors, then each router will send database description message. And this message contains link state identifiers only, not the details of the link state. We will send link state identifiers. It's like the primary key in the database. We send only the primary key. Like, I have these links. Do you have it? So the router 2 will try to use that to synchronize its database. So it will say, link state 1, I have link state 3, but I don't have link state 2. Okay, so that's a link state that I'm missing in my database. Okay? So database description message is used to synchronize link state database. And for that, we don't use we don't actually send the details of the link state, we send only the identifiers only. So we can send the entire database in 1 or 2 messages, right? Because we're sending only identifiers. So router 2 will say, oh, okay, I have link state 1, link state 3, but I don't have link state 2. So in that case, router 2 will send what we call link state request. I need specific link state, and in that message, I will send link state 2. I need the details of link state 2. Okay? So I'm requesting a specific link state information. So router 1 will send link state update, and link state update will contain link state 2 details back, all the details. Okay? And then router 2 will send link state acknowledgement. So that's the sequence. Once we know that we are neighbors, we need to synchronize our database using the database description. If we find that we are missing some of the link states, then we send link state request. You send link state update containing all the details about specific links, and then I will send you the acknowledgement to provide some reliable communication. Of course, this sequence can be broken, and any router can send link state update right away as triggered update, not as a reaction to link state request. عارفين دي طبعا. So link state update can be sent in a form of triggered update. So if a router has one of the networks and it goes down or it goes up or something like this, then this router can send link state update, which in that case it's the triggered update, not as a result of link state request. And in that case there is an acknowledgement. Yes. ماشي كده? So that's the sequence of these messages. So this is how the hello packet looks like. So the header, we talked about it. So this is the header. And of course there is like some security part, which you don't have to worry about. We'll talk about security later on. But this part in the header you don't have to worry about. So the most important is the area ID and the router ID and the type, which is in that case type 1, which refers to hello packet. And the hello packet itself is used to discover neighbors and establish adjacencies, in which case it sends the hello interval. It sends the hello interval in case of OSPF. اللي هو مقابل الhold time in the case of EIGRP, it was 5 seconds. Here is 10 seconds. Not that it makes a big difference, but the default value in the standard is 10 seconds. And the dead interval, which is the dead interval is the time that I have to wait until I declare a neighbor that it's down or it's not alive. And usually this dead interval is actually 4 times the hello. In EIGRP it was 3 times. And there is the important thing is what we call designated router and backup designated router. So that's a totally new concept that we need to talk about in the case of OSPF. This is a very important concept that we need to talk about in OSPF. So the hello packets content, it contains the message header, and it contains the hello intervals, which by default it's actually 10 seconds, and usually it uses multicast. So we'll talk about why we use multicast and not broadcast in a minute. And of course, for the case of non-broadcast multi-access networks, which is a special type of network that uses like a hub that connects routers. As we said, these hubs will form some broadcast domains, and if we send the hello packets with high interval or with high frequency, this might cause a collision. So for this type of networks, we need to reduce the hello interval a little bit. So for the case of EIGRP, we reduced it from 5 seconds to 60 seconds, if you remember. Here, we reduce it from 10 seconds to 30 seconds. It has to be reduced, okay? So we need to reduce the frequency of the hello packets in these types of networks. And the dead interval in that case is 4 times the hello interval by default. The system administrator is able to change all these default values in any way he sees appropriate. There is the concept of designated router and the backup designated router. So we talked about the fact that the autonomous system itself, in the case of OSPF, is divided into areas. Why? Because, of course, for link state, we use the concept of flooding. Okay? So flooding, of course, has overhead, and we talked about the implication when it comes to memory consumption, computational requirements, and so on, right? So OSPF tries to reduce that overhead by introducing the concept of areas. So we subdivide the autonomous system into areas. So for each area, you can think of an area as a cluster. So you are clustering the autonomous system. So each cluster will have a cluster head. So you have many routers in each area. A router is declared as a neighbor only if it exists in this area. ماشي? Not by the autonomous system if it exists in the area, right? So if you have like 2 routers like this, those are not neighbors. So those 2 are not neighbors, even though they are neighbors, but they exist logically in different areas, right? So they are not neighbors. So to facilitate the flooding of the link state update and the link state exchange in general, we have cluster heads. We designate one router, we call it a designated router. A designated router is essentially a cluster head. So in order to increase the fault tolerance, we actually designate a designated router and backup designated router. Backup designated router will take over if the designated router goes down or it fails for some reason. So this is for fault tolerance and high availability. We'll talk about availability from the concept of security in a minute. So all the packets sent by OSPF from any node will have to be sent to those 2 routers first. Okay? So that's why we use multicast. So if we send link state update in a form of flooding, it's supposed to be flooding, right? Which means that it has to go through all the routers. But for each node, it doesn't use broadcast and send it to all neighbors. No, it sends it as multicast to the designated router and the backup designated router only. And then the designated router will send it to all the other nodes in a form of multicast, and it has to go back through flooding to all the nodes. But for any node that's not a designated router, it has to send it to the designated. So this is the definition of a cluster head. A cluster head is actually made to do that. So the designated router has 2 jobs, 2 functionality. One, it facilitates the link state update flooding by allowing each router to send first to the designated router and the backup designated router, and then this designated router will act as a route and flood it to all the other nodes. That's one. 2, as you can imagine, it facilitates the inter-area communication. واضح كده? So it's used to facilitate the inter-area communication, because these areas are by no means isolated areas, right? So there has to be some inter-area communication between these areas. So designated router and backup designated router are used to facilitate this inter-area communication. So the backup designated router is is only for increasing fault tolerance. In case the designated router fails for some reason, the backup designated router will take over, and that's why it's current. It's involved in the communication in most of the cases, so that if there is any failure on the case of the designated router, it can take over seamlessly without affecting any type of communication. ماشي كده؟ طيب, forget about this part. So here بقى, we talked about if we use the database description, then we have some link states that are missing, then we send link state requests. So that's one sequence. The other sequence is that if there is any triggered update due to some change in the network, then we can send what we call link state update directly without having link state request. So a link state update or link state advertisement, both are terms used for the same thing. We are sending the detailed link states, not bad IDs only, no, the detailed link states, all the details about certain link state links, either as a triggered update or as a response to a link state request message. So that will contain all information about neighbors and the path cost and all this information. ماشي? So based on that, OSPF will exchange this link state update until all the link state databases become synchronized. So when I send database description to the neighboring routers and I see that we have synchronized the database, then this is the second step. So the first step is the hello. The second step is to form the link state database through the exchange of the database description messages.
Database description periodic?
Database description, no. Database description is sent during startup. It's sent very frequently during the start of the communication. So once we have the directly connected networks, we start exchanging database description to identify which link states we are missing between the databases, and we use this to send link state requests and link state updates and so on. So at the start, we will exchange all these messages: hello, database description, link state request, link state update, link state acknowledgement. We keep sending this back and forth many times, okay, until the link state databases become synchronized across all the routers. In that case, we can apply Dijkstra algorithm, which generates shortest path 3, and then this is step number 3, and then from there we can generate the routing table. So now we are in a stable condition. Then if a router finds that one of the links is down, one of the links came up, or something like this, then it sends a triggered update using link state update, and it sends it to the designated router and backup designated router in a form of triggered updates. Okay, so so the database description is sent at the start very frequently, but then later on routers tend to use link state update as triggered updates. واضح كده؟ Any other questions? واضح؟ أيوه.
Designated routers, they communicate with other nodes in other clusters?
Right, yes. Designated router, you can think of it as a cluster head. Cluster head معناها ان any communication has to go through the cluster. It's like an access point كده. So any communication within the cluster has to go through the cluster head. And not only that, if you want to communicate with the other area, then the designated router actually has to be in the loop. This router is the one that facilitates the inter-area communication. طيب, there is a concept of process ID. We talked about process ID in EIGRP. We called it a هتفكر? Autonomous system number. صح. And we said that autonomous system number has to match between routers in order for us to consider these routers as neighbors, right? So if we have a router here and it runs an instance with an autonomous system number 1, and a router here has an autonomous system number 2, those are not neighbors in the case of EIGRP, right? In the case of OSPF, the process ID has only local significance, and it does not have any meaning between multiple routers, which means that two instances with different process ID can still be neighbors. ماشي؟ عشان كده هنا we call it a process ID. We don't call it area number. We don't call it autonomous system number. We don't call it any of this. We call it a process ID. So the process ID does not have to match in order for us to consider these two routers as neighbors. واضح كده؟ So the only restriction is that you cannot start two OSPF instances with the same process ID on the same router. That cannot work. So here, you can start OSPF 1 on router 1, OSPF 1 on router 2, OSPF 1 on router 3. Okay? So these are instances that happen to use the same process ID on different routers. That's possible. They can be considered neighbors. Process ID it can be the same on different routers. There's no problem. But you cannot come here and say again router OSPF 1. So you will get an error message that you already have an instance with this process ID, so you cannot. So what is the use of process ID? The only use for process ID is to facilitate parallel computation. That's the only use of it for the case of OSPF, only to facilitate a parallel computation. But for the case of EIGRP, autonomous system number has to match for us to consider these two routers as neighbors. طيب, as we said before, أيوة.
Facilitate parallel what?
Parallel computation. Okay. So, as we said before, OSPF uses the bandwidth, the default bandwidth, as a metric, صح? So the way that we calculate the cost, the link cost from this bandwidth is by dividing what we call the reference bandwidth by the default bandwidth of the link. So that's how we calculate the cost. So the reference bandwidth is by default 10 to the power 8, which means 100 megabits per second. Okay, we divide that by the default bandwidth of the link. So if the link has a bandwidth of 100 megabits per second, what is the cost? 1, which is valid for the case of fast Ethernet. If fast Ethernet, the bandwidth is 100 megabits per second, this means that the cost is 1. This is the first row here. So if we have Ethernet layer 10 megabits per second, so the cost is 10. So you have T1 connection, for example, which is very common. T1 connection is a serial point-to-point, يعني leased line between two routers. So in that case, the bandwidth is 1.544 megabits per second. So we divide 10 to the power 8 divided by 1544000, and the answer is 64. So the cost here is 64, and so on. Okay? So the reference bandwidth is by default 100 megabits per second. So what if the default bandwidth of the link is more than 100 megabits per second? Well, nowadays we have 10 gigabit Ethernet, right? So does that mean that the cost can be less than 1? No. In that case, the network analyst needs to change the reference number, the reference bandwidth, to 10 gigabits per second in that case. So the reference bandwidth has to be the maximum bandwidth in the entire network. Okay? Otherwise, OSPF will consider 10 gigabits per second as cost 1. So because there is no cost less than 1.
ما في wireless interfaces في الراوترز؟
ما فيش لا في طبعا. The cost of the wireless interface عادي، ما فيش مشكلة. Why not? في based on the default bandwidth of the wireless. Of course, the wireless default bandwidth is tricky because wireless has variable bandwidth depending on the range or depending on. بس احنا هنا بنتكلم على ايه؟ default bandwidth, theoretical bandwidth. So if I want to send from router 1 to a destination here, okay, then طبعا this link is fast Ethernet. It has a default bandwidth of 100 megabits per second, so the cost is 1. And this link is by default T1 link, which has a default bandwidth of 1544000. So the cost is 64. Okay, so if I want to send from router 1 to a destination here, then I need to calculate the cost here, 64 plus this cost, which is 1, so the total cost is 65. That's the cost here. Okay, so that's how we calculate the cost. So just as we said before, bandwidth is supposed to be a bottleneck parameter, right?
Yes.
Yet we are accumulating here. Is that a discrepancy? Actually, no, because essentially the cost is the inverse of the bandwidth. The inverse of the bandwidth is essentially a delay. ما بيضحكوا علينا يعني هو أصلا هو actually it's a delay, not a bandwidth. So the delay gets accumulated, which makes sense because the delay is accumulated parameter. ماشي خد بالك بحته دي. طيب. So that's how we calculate the cost. So the end-to-end cost is by actually accumulating the cost of the individual lengths based on the metric, which is 10 to the power 8 divided by the default bandwidth. طيب ايه بقى 64 kilobits per second? This is called the actual bandwidth, not the default bandwidth. That's a little bit confusing. OSPF uses the default bandwidth. So a default bandwidth, for example, for any serial point-to-point link is 1544000 bits per second. But what if the actual physical link has an actual bandwidth which is different? Then it's the responsibility of the network analyst to set the default bandwidth of this link to 64 kilobits per second, because OSPF does not automatically get the actual bandwidth of the link. It will use the default bandwidth, which in that case 1544000. Okay? If the actual bandwidth is 64 kilobits per second, due to some physical limitations of the link, okay? So the link is not a T1 connection. It's a different type of connection. So in that case, the actual bandwidth is different. So in that particular case, the network analyst has to set this actual bandwidth as the default bandwidth because it's not by default. So that's what's explained here. So usually what you do is that you connect to an interface and then show interface. When you show interface, this link is supposed to have an actual bandwidth of 64 kilobits per second. If you show interface, you see actually the bandwidth is 1544 kilobits per second. Okay, which is different. And in fact, this is what's going to be used in the cost calculation. And that's why the cost of this link is set to 64, because it's based on 1544 kilobits per second, not based on the actual bandwidth. So, which might be inaccurate. Okay? So what should we do? Well, the network analyst should actually connect to this interface and say bandwidth 64000. Good. So only in that case, the OSPF will use the actual bandwidth for calculating the cost, and then the cost of this link will change from 64 to higher cost, which will be more accurate by in calculating the metric. ماشي كده? So that's the difference between actual bandwidth and the default bandwidth. So any questions? So that's the OSPF.